Okay, we have another short discussions, and thereafter we'll move to the discussion on packet routing. Okay, probably you have also come to know from other sections that I don't take the attendance into account. I mean, I don't know the way. I mean, why is the attendance so poor today? Why is the attendance so poor? Many people, only few of you are here, right? Others are on the way, or what? I mean, or they won't come to the class. Huh? Oh, okay. So I actually already told the other sections that I won't take attendance any longer. In fact, I don't take the attendance record into account. I give full points on attendance. I just pretend to keep some people in the class. That's it. I mean, this is not only for your case. I mean, in the previous years also I did the same. But the point is, I mean, some of you will probably are now repenting. They know why. Okay, what I have done. Why I have come to classes all these days. I mean, after declaring it, it was my first class with another section, and the attendance was very poor. I mean, only a few people were there in the class. I don't know what may happen to you. But my point is, you see that in the new system, already implemented for first year, there's no marks on attendance. And the change in the exam policy was actually initiated from our department. And personally, I actually took the initiative back in 2022. We first sent, in May 2022, we held a few meetings in our department. This is something I did after taking over the charge of accreditation. I found that the accreditation requirements also better match. Okay, I mean, they don't have anything really on attendance, so it better matches. So then I also, took it as an opportunity because, yeah. Well, we're supposed to apply for it. There are two deadlines every year, January 15 and July 15. Last January 15 we were supposed to apply by, but because of the unrest in the campus, we failed to do that. So before next July, inshallah, we'll apply for it. It may not help you, but in future, it will be a requirement for the students. Right now, actually, you see that all of our graduates get, chances in the top level universities of the world, meaning that they, recognize our degrees completely. Even the top tier universities, there are no problems when you apply. Okay, for admission, there is no question. But because many other universities are not also accredited yet, the preparation for accreditation takes a while. Okay, in fact, we started preparing for it around 20. It's little longer than 3 years. But originally, we should have OB-based studies for 4 years. Then you apply, and then you show that all these 4 years, all these graduates have come out with. Okay, so actually, it's a long preparation. It's a long preparation. But you can also apply beforehand and show that some of the graduates are already. We're going to apply with showing that 18 batch and 19 batch have fulfilled the OB requirements. So let me finish. Just so that's why it takes long for any university to apply. But the point is, in the course of time, you'll find that almost all universities, all these programs are already accredited. I mean, they have gone for this accreditation requirements, they fulfill the requirements, and they are also accredited. And when it will be the case, then some universities where you apply to, they also will start checking whether the program is accredited or not. That may be 10 years from now, or maybe a little earlier, nobody can tell you. But at some point of time, it will be the case when they will check whether the program is accredited or not. So for you guys, or even the graduates in near future, frankly speaking, this accreditation will not help you anyway in your life. Probably, there is very small chance. Okay? But it's a long process. We have to start the journey ahead of time. Yeah, good. Sorry? Yeah, that's what I say. I mean, most likely you won't experience any benefit. Okay, because you'll find that your degrees are recognized fully everywhere. Accreditation is kind of recognition. Your program fulfills this requirement. But it is to some extent, but right now it's just, a binary decision. Whether you get the accreditation or not. Even until recently, it was like our two programs are accredited, mechanical civil. So civil got accredited for 6 years. That's the maximum. Mechanical got for 4 years. So it was like, say, civil of Buet got first it for 4 years. Then they applied again to get for it longer. So they get second time, in second attempt they got it for 5 years. So it was like how sort of indicative of your quality. But right now they have made it just binary. Everybody 6 years, whether you get it or not. So quality is rather indicated by ranking, say US ranking or whatever. And here it is like you have a recognition or not. Got it? Although, there are certain requirements, they check how well you are fulfilling the requirements. Okay, so there is a quality, definitely, inherently. But the decision is just binary. Okay, black and white. Okay. Anyway, we're running short of time. We have a lot of content yet to be covered, important concepts yet to be covered. And I want to have an extra class. Are you supposed to have that? Yeah, please make an arrangement of an online class, including both section A and B. Okay? There is small difference in synchronization, but I'll make that up. Online class, because in Ramadan it's very difficult to schedule. Okay? And we may have to schedule another extra class, because too much materials need to be covered. And I cannot go too fast, because you have to understand. Now this is a principle used, say, TV, radio, which tunes to many different stations for catching analog signal. And superhead principle, the receivers, when you use the principle, it's called superhead receiver. So I'll explain it using the example of our normal radio broadcast, which uses, AM or FM, and different stations use different frequency ranges, so it is frequency division multiplexing. Now, for speech, for human voice, up to your microphone collects human voice, and then the waveform is, you do a Fourier transform on the waveform to get the components in different frequencies. So you'll see the powerful components lie within 3.4 kilohertz. although there can be components up to 20 kilohertz. But by powerful, I mean in the Fourier, after get in the Fourier frequency domain, you have different magnitudes, right, at different frequencies. So the high magnitude components are mostly within 3.4. So if you capture up to 3.4 all the components and cut off the rest, after reproduction, it is not distorted significantly because you've captured all the parts. But to cut off the rest, you need a filter. There is no ideal filter. So filter has certain slope. So you need a slope for your filter. So rather you have to allow little wider. So for human, to capture human, up to 4 kilohertz is taken. So the bandwidth for requirement for human voice is 4 kilohertz. However, the audibility of, human audibility is also up to 20 kilohertz. So if there are any generations, it can detect. Musical instruments generate also powerful components beyond that, and typically up to 15 kilohertz. So to capture music better, you need a wider bandwidth, not for voice, but to capture music. So it can be made little larger. Like in the case of FM, it captures initially, so that's the information up to 15 kilohertz. So in FM, the music reproduction is much better. But information bandwidth is very critical because that tells you what the actual bandwidth would be. So it can be much wider. For AM, it is made little larger than 4 to capture some music, better, and it is either 4.5 or 5 kilohertz. So that is something we are indicating using W. So is the base. For AM, you know what it is, amplitude modulation. It uses double sideband amplitude modulation with carrier. The carrier is not suppressed. So the total bandwidth you require, you have up to, when you put it on a carrier, you will have, for each of the frequency components, you will have components around the subcarrier. So total bandwidth twice W is required, right? And for FM, it depends on how many Bessel function components, because the resultant components come out in the form of Bessel function. And it depends on you how many components you would take. Based on that, on both sides of the carrier, you will have certain bandwidth. Now let's see what numbers they use for the bandwidth. So it will be for W, but since it's just little different in different countries, let me go through this part first. From ITU, International Telecommunication Union, there is a definition of regions for the world, 3 different regions. And you see we are in region 3. Region 1 and 3 have pretty much the same kind of choices, but region 2 goes differently, not only for these cases, like for miles, kilometers, pound, kg, they go differently. So here also region 1 and 3 have uh, 9 kilohertz total bandwidth for AM. So W is 4.5. 4.5 W, so the total bandwidth is 9 kilohertz. So the AM radio stations have actually carrier frequencies 9 kilohertz apart. When you tune, there can be different stations. Well, only few stations may actually be transmitting. but there are possibilities at every 9 kilohertz. First, in North America or Latin America is 10 kilohertz apart. So this is the frequency ranges possible from carrier frequency from 531 to 1602 with 9 kHz spacing. Here 530 to 1700 with 10 kilohertz frequency. So when the carrier frequency is 530, the actual range is 525 through 535. 530 is the center that you tune to on the radio when you tune to. Okay. So these are the possible ranges. Any radio station must be within this range. For AM, the bandwidth is fixed everywhere to 200 kilohertz. So now you can calculate how many base cell function components have been included. Okay. W is 15 2D plus 1 times W, and that must not exceed 200 kilohertz. And the frequency range is 88 through 108 megahertz. So at every 0.2 megahertz spacing, you can have another base station, another radio transmitting station. So if you scan through all the possible stations, it scans through, you may have checked from FM at every point, 88, 88.2, this it keeps checking, right? Now that principle of superheat. Well, when you receive the signal, it comes, okay, so I'm sure now that information has already spread that I don't use attendance for marks. You see the attendance today? Yeah. And some of you probably don't know, are yet to know. Okay, right? Okay. So now you make intention that you won't make this mistake. Okay. I mean, I thought people would come here to learn something. In the elementary school, we can bring people, I mean, forcing them to, okay, using attendance or whatever. But at this level, you should come on your own with your own, anyway. Now, the power is very low when you receive, so you first have to amplify to be able to work on that. The problem is, for amplified design, the gain increases if your bandwidth is small, but if you have wide bandwidth requirement, the gain drops. The gain bandwidth product is pretty much fixed. Do you remember? For amplified design, do you remember that? Remember it? You don't remember? See, I don't teach in first year and second year because in third and fourth year people have some background, they are mature. But this also has a problem. You see, in first year, even if I don't take attendance, students would come, but in third or fourth year, probably, if I do, people are not coming in. Okay, too smart. People are over smart there. Okay, you don't remember for, amplified design. Say if you have pick a transistor with high beta, high gain, okay, then you'll find that its bandwidth is small. And pick another transistor with low beta, similar type of transistor. With low beta, its bandwidth will be wider. Okay, beyond that, it does not offer this gain. Okay, it has certain bandwidth. So for amplified design, bandwidth gain product is pretty much fixed. Now, in the case of radio stations, you don't know which station you tune to. So, FC, what is duster? There is no duster. So, you may be capturing from here, or you are tuning to, I mean, these are all FC, or here, 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 you don't know where you're tuning to. So after capturing the signal, you need to amplify. So the bandwidth has to cover all the possible carrier frequencies. That's a huge bandwidth, say from 500 kilohertz to 700 kilohertz huge bandwidth. And for this large bandwidth, the gain would be very low. Oh, that's a problem. But actually, once you tune, your information lies within a very small bandwidth. So after tune to your intended station, you don't actually amplify information over large. Actually, over very small bandwidth, you amplify. But that the location of this small bandwidth is not fixed. So that's why you need large bandwidth coverage on the amplifier. So if you could translate to some fixed location, then you could design an amplifier with high gain. This is what is done in superheterodyne principle, or this technique is called superheterodyne. There are two stages. The first stage is called radio frequency or RF amplifier, which has this kind of large bandwidth support. Oh, using. No. When you are tuning, I mean, you have some fixed amplifiers in your receiver. The amplifier property cannot change. Okay? You can work on your signal, but amplifier property will not change. You cannot manually change the amplifier. I think it will be clear shortly. So the RF amplifier covers all the possible radio stations, all the possible frequency carriers. So at this level, the gain is very small, but it helps to some extent. This XT is at least, I mean, it has at least enough power for you to further process. Okay. To some extent, it helps. Okay, then there is a technique to translate. So maybe you have picked from here, or from here, or from here, whatever you pick, it translates to the same frequency. Okay, it changes the frequency and brings it to a fixed frequency. So then around that frequency, you have just that twice W bandwidth. Okay, whatever bandwidth you had. So since it has a fixed location of frequency, after translating using superhead principle, now you can use an amplifier which requires this small bandwidth, so it can have very good gain. Let me show you how it works. As you tune, I mean, this dotted line shows that you're changing here the carrier frequencies, the frequency that you are currently capturing. Now there is a local oscillator. There's an oscillator which generates a sinusoid, and it's called local oscillator. That generates sinusoid with certain frequency, and this frequency also changes together with your tuning here. Now the frequency it uses, F1, is equal to whatever frequency you have there, plus a number called intermediate frequency, IF. So for the local oscillator, the frequency is like FC plus FIF. Okay? Now generate that a sinusoid. Then you send this signal and your information to a mixture circuit. it's called mixing operation, or the circuit is called mixture here. So your information and this local oscillator sinusoid. So this mixing operation is pretty much like the modulation that you are familiar with. And the result has two frequencies, the addition of these two and subtraction of the two, like you have for the sidebands. So it is called mixing operation, but it generates two new waves out of the mixing. One with the frequencies summed up, the other with the frequencies subtracted one from the other. So we have here, say, FC, and here FC plus FIF. So if I add them, I don't have any duster today. Okay. So this one is local oscillator frequency. So that we have to add to FC, and then we also have to subtract FC from here. So if you do that, then we get 2FC plus FIF and only FIF. So this FC maybe we had here FC. So after mixing operation, we get 2FC plus IF so you had different frequencies around. Each of the components now generate some components around this carrier and also around this carrier, right? And these two are far apart. These two are far apart. Now you see that if IF is fixed, it's a fixed frequency. It is for AM everywhere the same worldwide. For AM it is 455 kilohertz, for FM it is 10.7 megahertz. That's a fixed number. So whatever your FC is, FC can have many different numbers, but it is shifted to this location, which has a fixed number. This one has a variable position, but it is far apart. Thereafter, you feed it to an amplifier, which has a small bandwidth requirement. Oh, sorry. When you feed it to an amplifier, this is called intermediate frequency amplifier. It has a small bandwidth requirement, only this much. So IF amplifier can offer very good gain. This one has a very low gain, this one has a very good gain. Now you actually do the necessary amplification. So this is called superhead principle. But you see that this amplifier has a bandwidth coverage like this. So you actually fed this one too, but that falls far outside the bandwidth of the amplifier. Beyond the bandwidth, the amplifier, amplifier bandwidth is like this. So you have very small, gradually the amplification drops, and after certain frequencies, you have almost no signal at the output. So this part is not, you don't get this part at the output of the amplifier, or even you can use a filter here to cut off this part. Okay, so that's your amplifier output, which you then demodulate. Okay, after you demodulate, what do you get? Where is it located? You see that the actual information is, say, FIF plus W, and here FIF minus W, right? And after you demodulate, you get it from 0 through W. That's the original information. And then you can use the low pass filter to cut off anything unwanted. Yep. So you reproduce the sound. It uses double sideband with suppressed carrier because then the receiver cost is minimized. It's the simplest modulated transmission. Simplest double sideband amplitude modulation. The receiver, just a diode and capacitor, is enough for you to reproduce. Probably remember that you have an envelope representing your information. So a diode can cut off the negative side. Then a capacitor can trace the envelope. Okay. Although the real circuits are a little more complicated, but still the receiver cost is so since they transmit from one location, but many people will be receiving using double sideband suppressed with carrier, they minimize the receiver cost. I mean, in those days, even this radio receiver was not affordable to many people. Now this part you already don't have here, because the amplifier has a bandwidth coverage like this, right? This part maybe little more because of the slope and whatever you cover here. This part never falls into the bandwidth coverage. So it's not, you don't get it at the output. Okay. Now there is one possibility theoretically one problem with separate principle. I'll explain that, but that problem does not occur in practice. If you have another station transmitting at a frequency FC plus 2IF, FC is the intended carrier frequency that you want to listen to. But there is somebody else who is transmitting at the same location with a frequency FC plus 2FIF. Then this signal is called image signal, which can be a problem potentially. How is that? Let's use an example. Right? Your intended carrier frequency is 100 kilohertz. Then the local oscillator is generating 1455 kilohertz. So after mixing operation, you get the summation and subtraction. So you get 455 kilohertz component. So you reproduce from there. But if there is another transmitting station at 100 plus twice of 455, twice as much as 455, there is 1910. Then what happens? This signal also combines with this local oscillator. It is also captured because RF amplifier lets everybody in. So it is also mixed with the local oscillator frequency in the mixture circuit. And then you generate summation and addition of these two. What do you get out of the two? When you subtract, when you add, it will be different. But when you subtract, it also generates 455. 1910, and you subtract 1455 from there. It just so you get actually from this unwanted station, you also get a signal at the output of the mixture. So that will be definitely interference, or it may cancel. So this, but this is called image signal problem. I mean, this signal is called image signal. But this problem does not occur. You see, it requires FC plus 2 FIF. In the case of FM, what's your FIF? Remember, these numbers you have to memorize. Okay, the numbers we have been sharing here. Few things you have to remember. Few things you won't have to, like the MCS table. You don't need to remember those numbers, but you need to follow how things are changing there. Not the exact numbers, but how things are changing there. Okay, that's the reason. But few things, like I showed you the modulation levels available at different technologies, 2G, 3G, 4G. These things you need to remember. How many MCS levels you have in 2G, okay, HSTPA, LTE. Because when you join the industries, you'll see that people know these things. But those tables, they don't remember. Okay? If they need anything, they look into that. But when you see, we had a slide depicting what modulations levels are permitted in which generations, like H uses GMSK and 8PSK. LTE supports QPSK 16-QAM and 64-QAM. These things we included in a slide. You need to remember, because people know which modulation levels are supported in 2G, 3G, 4G. Okay? How many MCS levels are supported? But some data we shared here are not for you to memorize. Here, the numbers you need to memorize. Okay. Questions? If not, we move to the next slide. There are so many things to cover. How packets are routed. Different countries implement little differently. But one example can help you get the idea. So use the example of our country. For any digital communication means your original information is in terms of zeros and ones. The information is packetized and then sent, but there are basically two ways to route your information: circuit switching and packet switching, CS and PS. But however the name suggests, packetization is invariably done. So circuit switching also uses actually packets. You may be sending the bits one after another, it's a bit stream, but conceptually there are certain limits. For up to this limit is considered one packet, then another packet or block, whatever you call packets. Okay, so there is certain conceptually there are some packetizations always. Now there are basically two different ways. So it's not a packetization, rather how you differ CS and PS. In the case of CS, you first reserve your resources to send the information. So as you say, make a call or you set up a data station, you first reserve the resources and then start sending the data. Until you terminate your call, your resources are dedicated for you. Nobody else is going to use the same resource. So this is called circuit switching. And up until today, we have been using CS for voice calls, except the negligible use of VoLTE in our country. So voice and SMS uses CS, but the basic LTE does not support CS. CS is getting obsolete. Why is it so? Well, the other option is packet switching, where you don't reserve your resource. The resources are available. When you have some data available, you request for resources, and then resources will be allocated if resources are available then. And then you use the resources. Once you finish sending your data, the resources are taken away. And somebody else may use the same resource. So the resources are not reserved, it is not dedicated for you. So different people. So this way, you see, for example, say when a guy calls his wife, okay, he's talking to his wife. So it's a, bidirectional way. So resources are allocated both ways, right? But one of the two links is left unused almost most of the time, right? You know what I mean? When a guy talks to his wife, one of the two links is almost not used. You know what I mean? Are you getting the point? You're not getting? Yeah, how would you get it? Because you're not married yet. Yeah. You need to get married first to understand the point. Okay. After you get married, it will happen. When you talk to your wife, I said that CS is used for voice. Okay. So means that it reserves the resources for transferring information. So you send your voice package to your wife, but so there are resources reserved both ways. But the real life is like one of the two links is almost not used, and that other link is overcrowded. Okay. So you're not getting the point now because you're not paid it. Well, you know what? The guys think that, after getting married, my life might be hell. Okay. And what happens after he gets married, you know? He thinks that, okay, my life might be hell. But in reality, what happens, when he gets married, he just confirms it. Okay. Well, it doesn't help. However, I also discouraged people in the previous years. It didn't help. Yeah. Nobody is enough intelligent. Okay. So now, if you, as in the past, when people started using the communication, then there are very few users. The total requirement for, sorry, the total requirement of information transfer was limited. But now, so many users willing to send so much volume of data. So now, the efficiency of the resources, of the use of the resources is far more important. So it's no longer, it's a luxury now to reserve a link dedicated. Okay, so CS is already, you can say it is getting obsolete. From 4G onwards, there is no support of CS. It's all PS. In this case, there is a disadvantage. Like since you don't reserve it beforehand, when you have some packets ready for transmission, you don't find any links available. All the resources are already occupied by other people. So there can be an availability of resources. So you then keep buffering and wait for the resources to be available, but you don't get any chance, and at sometimes buffers overflow, so you lose packets. This is called packet drop. And so some packets are dropped means the quality of your service is degraded. So packet drops can occur for packet switching and difficult to maintain quality of service. On the other hand, for CS, packet drops are negligible because you ensure the availability. So QS can easily be guaranteed. The voice is still the source of the good part of the revenue for the operators. So they have to be careful. They have to maintain the quality. You see, sometimes you call on WhatsApp, which uses PS. Okay. Like I said, that voice and SMS, for the time being, consider up to 3G. Voice and SMS uses CS, and all kinds of data uses packet switching. Is the case for 2G and 3G. Say you surf the web, you send email or whatever, all kinds of data services use packet switching. Voice and SMS. But we had actually this voice service for many decades. So there is, huge investments developed over the decades, a well-established and very reliable infrastructure to route voice information around the globe. So overnight, you cannot just leave that infrastructure and go for a new solution. So that's why there's a gradual transition. Gradually, people are transitioning to a smarter solution. And this is why LTE did not include CS, but it knows that it cannot start PS for voice service readily. So there is a solution included in LTE. Like there are actually quite a few options there. The most popular one is like what we are using, and I told you before, that when you want to make a call, it puts you back to 2G or 3G. It puts you on 2G or 3G. And then once the call is over, it puts you back on 4G. Okay. So for the time being, use this is called circuit switching fallback, CSFP, circuit switching fallback. So CS is not used in LTE, but LTE uses what is called CSFP, circuit switching fallback. For voice services, the operators, there are different operators, and when a Grameen phone user calls another Grameen phone user, then the packets flow between them throughout the Grameen network. It doesn't go, the packets don't go beyond Grameen network. Okay, that's the case. Previously, in the early days of this structure, there are also interconnections among the operator, direct interconnection, between Grameen and Robi, Grameen and Teletalk and Robi this way. So when Grameen user calls Robi user, packets could just route between the core networks of the operators. But later, government is not the same everywhere. In our country, our government imposed that the packets must be routed via a node which is implemented by another vendor when it's between two different operators. So now when a Grameen user calls Robi guys, the packets go via IC. This interconnection, this is called ICX, interconnection exchange. It goes via ICX. Okay. So the same operator, packets don't go via ICX, but different operators, then it goes. There are 26 ICX companies. And if you make an international call, then the packets are routed first to ICX, but then it goes to something called international gateway. This is another operator. There are probably 28 IGW. Okay. These numbers may have changed little bit recently, but in last 1 or 2 years. For data services, I could update to the present number. Later we'll discuss data. For voice, these numbers may have changed little slightly, or may not. It may be 28 or okay. Anyway, so your packets first goes to IGW, then it is routed via some international carriers. So when you're talking to someone in UK, probably the carrier will be British Telecom. There are many international carriers who provide services around the globe for money. So they charge you. So there are negotiations or deals between IGWs and different international carriers. Large IGWs have deals with more international carriers, and they can cover more countries in a easier path. So these are some names of international carriers, and okay, so that's how information is routed. What time is it? Any questions? But later, government imposed the existence of, for international calls, imposed another node here called iOS. This is something because there are a lot of corruptions to evade the government charge on international calls. I mean, people tried to evade the government charge or tax on international calls. So they had some negotiations with some, say, some parties in Singapore or something. So they could route the voice information to there, and they helped routing the information. But in that case, they actually used, while to route the voice packets to other countries, I mean, furtively, without letting the local authority know, they had to actually put it into IP packets, I mean, packet switching they had to use. So that's called VoIP. Normally, VoIP is not, I mean, VoIP you can use, like WhatsApp uses VoIP anyway. It uses packet switching. But they put it again, and they evade the tax part. So that is illegal. So to actually stop this evasion, tax evasion, government imposed another node here, iOS. Before you send it to IGW, it goes to, so government can monitor from there. Although they say that iOS has all these reasons, okay, please go through them. I'm not telling everything. And there are 7 iOS companies. This is the list of the iOS companies. And to stop here, so please arrange an extra class for section A and B. Okay, okay, it's all right at your convenience. And set up a date for our 3rd class test. In the last week, we'll arrange our 4th class test, where you'll have to solve a complex engineering problem. It will be a long test, probably taking up half an hour.